YouTube. Okay, so welcome to the YouTube people as well. And welcome to the 304 of you who are already here on this Friday morning. It's 11:09, so I'm a little ahead of the game here. I just want to say it's warming up in Toronto. It's going to be warm for the next few days, right, as we start our reading week, so that's really lucky. I might as well share what's going on here, what the plan is for today. Get my Zoom all set up. So there's my PowerPoint slide. We're going to do a quick little review of Chapter 7. We're going to get into continuing on Chapter 8, trying to finish it up on Monday when we come back. Today, a lot about center of mass. And this is showing what's called Grand Jete, where in ballet, where a dancer jumps up and, of course, her center of mass has to trace out a parabolic trajectory, but what she does is lifts her legs in such a way to bring her center of mass up and then down, even while her head is just traveling straight along. So it almost looks like she's floating. So let me get my Q&A up here. So the final assessment is on December 17th, I believe, Maria. There's nothing happening on December 15th. If that helps there. Let me get my chat window up. There it is. Raven, are you a ballerina? Or are you in ballet? Dancer? Ah. Okay. I imagine it is very difficult. So let's do, just to stick in routine here, I should put on a face filter for today. Polls, watch polling. So feel free to vote on that. Again, there's limited choices on Zoom, so I just putting the ones that I'm willing to wear. Just it's a little bit silly. Got to have routines in life, right? So keep things interesting. Someone is suggesting maybe sunglasses in honor of Joe Biden. It's a pretty smart idea, but it's up to you. Again, it's this is a democracy, at least. Okay. Yes, well, we'll see what the vote is. You got 5 seconds to click in a choice. 3, 2, 1. It's going to be close. Close elections, it's not a good thing. Okay, so what did it end up being? Oh my goodness. So 110 of you voted for Bunny Rabbit. And the next one up was 98 of you voted for Happy Sprout. So, well, I guess we're going to with Bunny Rabbit. Let me just find it here. Yeah, filter. Okay. It's down near the bottom somewhere. Bunny Rabbit. Okay. That's your prof. All right. Okay. So actually, I start with another poll, actually. And this one is got 6 choices on it. So, a string is attached to the rearview mirror of a car. And you're in the car and you're looking at a ball, which is hanging on the end of the string. The car is turning left on a circular horizontal path at a constant speed. Maybe it's just a slowly curving highway or something like that. It's not speeding up or slowing down. What direction is the ball accelerating? Is it up to the left, to the right, sort of a diagonal up and to the left, diagonal up and to the right, or F, the ball is not accelerating? Some of you are calling for a recount and saying that the election was rigged. You're making me laugh here. Okay. As for this one, there is one correct answer because it's the dictatorship of Mother Nature. It's one way to do this. Let's do 5 more seconds. 4, 3, 1. Yeah, oh, so someone was asking what's the reference frame. So this is relative to like the Earth, okay, the lab frame. It's a really good question from Kaylani. I don't know if that changes your answer. Because yeah, in the reference frame of the car, it's not accelerating. That's a really good point. So a lot of people were voting for B, horizontal to the left. So that's definitely what I was looking for here. So certainly in the reference frame of the car, the ball is not accelerating, but in the lab frame, like the Earth frame, which is where I want you to do your Newton's laws, it's accelerating directly towards the left. And we can sort of show this. Let's look at another one. Another quick question here. I'm going to click real. Get my zoom together here. A string is attached. The car is turning left. Which of the following lists all of the forces directly acting on the ball? So these are the forces that you would list in a what you would draw on a force diagram of the ball. So you'd have to put the 1-on-2 notation of whatever the external object is. It's providing the force on B, the ball. So I want a complete list of all the forces. Just a little review for you. And Mircea, yes, it's the ball is accelerating towards the center of the circular path that the car is on. It's on a horizontal circle, so that means that directly off towards the center of the circle is the direction of the acceleration. That's a really good point. And maybe this is chapter 6. Sorry if I've got the chapter wrong. Okay, let's end it and we'll just, it's definitely a review. So 63% of you are voting for tension and gravity, which is exactly right. So, and the way I try to remind myself is when I'm drawing a force diagram, I try to put these subscripts. So the force of gravity comes from an external object, which is the Earth acting on the ball. The tension comes from an external object, which is a string acting on the ball. The centripetal force is the net force. This is centripetal. You don't draw the centripetal force on the force diagram. So the net force, the sum of all the forces, is something you kind of draw to the side. And then what you would do is you would define y to be up, r towards the center of the circle, and then a sub r would be the sum of all the fr forces divided by m, and that would be v squared over r. And so, all right, also the sum of fy is equal to 0. And yeah, as for why you don't draw the F net, I never draw it just because it's reminding me of where the acceleration is. It's not an extra force. The F net, the centripetal force, has to come from forces that are acting on that object. If you draw the net force also on the diagram, it just makes it really confusing. You're drawing the sum of all those forces. Okay, we're doing a lot of pulls here. Let's do another quick one, just to kind of get us into the mood here for continuing on chapter 8. And it's making me feel a little hungry. Let's just give you 10 seconds to click into this. Yeah, F should be in my stomach. Okay. I'm going to quickly just share this. So most people are saying C, which is correct. So the idea here is that anytime you have an object, a rigid body, where all of the points in the object are fixed relative to each other, such as a donut, all these sprinkles don't really move around relative to each other, neither do the molecules within the donut, then you can find a center of mass. And that is going to be the weighted position of all the mass in the object. And it doesn't have to actually have any part of the object touching it. So in this case of the donut, right in the center, where the hole is where the center of mass is. So center of mass, say of this triangle or something, if you have an object which is made of particles, each individual particle, which we could label with a index I, has a mass m sub I. The center of mass would be the sum of all the masses of all the particles times the positions of all the particles. So in the case of the x coordinate of the center of mass, it's the sum of all the masses of the particles times their x coordinates, and then divided by the total mass. And for the y, you do the same thing. mi times yi, you sum that up all over all the different particles, and then divide by the total mass. And so if things are symmetric, you end up getting it right in the geometric center. There's no y symmetry here, so you just have to actually do the sum. And then she mentions in the book that calculating center of mass is much like calculating your grade point average. Marks in like a full course, like a math course, would be count twice as much as marks in a half course, like Physics 131. And so particles of higher mass have a higher m sub I, they count more. They can drag the center of mass towards them than particles of lower mass. So an unconstrained object, for example, one that's not on an axle or a pivot, on which there's no net force, will rotate around its center of mass. That's one of the neat things about it. Center of mass remains motionless while every other point undergoes circular motion around it. So that's if it's way out in space or something. And then if you were to throw an object which is rotating, then the center of mass would be what traces out this point particle trajectory, the parabola, even as the rest of the object can rotate around it. And the other thing about the center of mass is that that is also where the gravitational torque comes from. So when you're calculating torque due to gravity, you may treat the object as if all of its mass were concentrated at the center of mass. So the net torque due to gravity acts at the center of mass. And I was talking about lever arm. I'll talk about lever arm a little bit last time. The lever arm of the gravitational force is the perpendicular distance between this force line and the rotation axis. So this, she calls it axis of rotation. Okay, so there's the axis of rotation. There's this force of Earth, Fg, on the object. And it's pulling down, and this is going to be the torque in this way. It'll be negative torque. So when an object with some distributed mass is in static equilibrium, the torques produced by gravity on the objects on each side of the center of mass have equal magnitudes. So the trick here, which you're going to be using in the team-up quiz, is to choose the support point is the center of mass. And I'm going to choose it also to be the axis of rotation. And so what you'll have is that if there's some sort of mass of the metal and some sort of mass of the wood, metal and wood part of this handle, then this will be this distance. Maybe call this M1 and call this M2. Then this distance would be X1 from here to here, the sort of the center of the handle. And this distance from the center of the metal knife to the pivot point would be X1. And so this one is pulling it in this direction. This would be, I guess, a negative torque because it pulls around the axis of rotation in a clockwise direction. And this would be in counterclockwise, so this would be a positive torque. And so what happens is that the sum of the torques is equal to 0. You'd get M2G times X2, that's negative, and then plus M1G times X1, and then the G's cancel. And if you sort this out, and like I say, this is going to be important for your team-up quiz, you get that these torques balance. So M1 times X1 is equal to M2 times X2. And so, and I guess another way, if you want to rearrange that, you could say that M1 over M2 is equal to X2 over X1. So basically, since X2 is greater than X1, this means that M1 is greater than M2. The handle is heavier. Okay. And I can also sort of do it with this. Let me just turn off the share for a quick second here. So these different masses are talking about the masses of the different points. So here we have a little hammer, and I've actually put a little dot here of where I think the center of mass is. If I hold it right under the center of mass, then the torques on each side sort of balance out. Okay, so we have the same amount of mass on each side and the torques balance. And then the other thing you can do is you can kind of throw it and see that it's rotating around that center of mass. Oh, you can kind of see that. That's my quick little demo there. Go back to share screen too. Sorry. Every time I turn off the screen share, get my Zoom working again. Jerry, did you have a question?
Yeah. So I was. Can you go back to the hammer slide, like where you first talk about the axle and center of mass? Yeah, this one. Like the next slide. Yeah, this one. So wouldn't the center of mass always be the axis of rotation?
Well, no. Certainly, if you have a door, for example, where you put a hinge, you can have the center of mass of the door not be around the axis of rotation. It's just when it's unconstrained, right? It's not hooked to anything.
Okay, so like if during a trajectory motion, let's say I throw something up and over, and that center of mass is going to be the rotation axis, right?
Exactly. Yeah, that's exactly.
Then the torque exerted by gravity is going to be 0.
Right. That's the reason.
Oh, I see. Okay, thank you, sir.
Yeah, sure. And Josephine, you have your hand up.
Hi, can you hear
Hi.
me?
Yes, I can.
So for the slide before this one,
This one?
yes, this might be a silly question, but what exactly is this formula for? Is it for the torque or the center of mass?
This is just for center of mass. You're trying to find the location of the center of mass of an object. And that will be where the gravitational torque comes from.
Okay, so on like the next two slides, the one that you just solved.
Yeah.
So this formula then, like, how are you using it if it's for the center of mass?
Yeah, that's a good one. So it would put the center of mass at that center point. Like if I have the origin there or something like that, then m1 times x negative x1 plus m2 plus x2 would end up being 0 because the center of mass is at the origin.
Okay, so the force would be acting on the center in this question?
The gravity, the gravitational torque is acting at the center of mass, and that's why it doesn't rotate it one way or the other.
Okay, thank you.
Okay. Yeah, it's a really good point, is that this, once I canceled the g's, this ended up looking a lot like the equation for center of mass. So I'm gonna actually send you guys over to this team up quiz on chapter 8, which is all about these center of mass and rotations, and hopefully you can work together and listen to each other instead of me. For a change, you can see under module 4, it should show up now on team up quiz module 4, chapter 8, and click the go to tool. So don't start it until you've chosen a driver in your Microsoft Teams. So you should log into Quarkus. I forgot to put on the help center, but I'll go and do that now. Non-drivers, it's the same sort of routine, just wait, driver, go into the quiz, start a new session, then tell all your friends what the session ID is. Non-drivers, once you get the session ID, then you go and enter it, you click join session. And after everyone is in the team up quiz together, that's when you can chat about the questions, achieve a consensus, and move through it. So I'm going to put myself on mute here and try to go over and open up the help center. Sorry, I haven't quite done that yet. just set a 60-second timer before we resume. Okay. All right, everybody. It's looking pretty silent out there. That might have been a little more of a difficult one. I want to go over these questions. So question 1 was asking about two objects, mass m and 2m, are hanging from the opposite ends of a horizontal beam. So we can just sort of call this one maybe m1 for now and m2. And here they are hanging from a beam. It's a uniform beam. So the center of mass of the beam is right in the center. I haven't drawn that very well. But then you've got sort of m2, which is some distance x2 from the center. And m1, just some distance x1 from the center. So torques must balance. Choose axis of rotation. You can choose anywhere we want, but let's choose it to be the center of mass, or the. Okay, so, and once again, the sum of the torque, sort of like we did before, is m1 g1, or g times x1, minus m, wait a second, that's gonna be wrong. Yeah, that'll be clockwise, counterclockwise, and this one would be counterclockwise. And g's cancel, and you get that m1 x1 is equal to m2 x2. So x 1 over x2 is equal to m2 over m1, 2m over m equals 2. So what it means is that this object m1 is twice the distance from the center of the beam. So let's see. You guys still out there? I feel like I've sent you off into your own conversations. Just good. You gotta be there for each other. Question 3, or sorry, question 2. You got two objects, masses 6 and 8 kilograms are hung from the ends of the stick. So this is the same sort of thing. If you set this chord equals the axis of rotation, wherever that is, then again, m1 x1 equals m2 x2. So if we set this one equals m1 and this one m2, then what I would say is that 6 x1 is equal to 8 times x2. I can divide both sides by 2, and I could get 3 x1 is equal to 4 x2. So the distance from the center, we have to find something that times 3 times something equals 4 times something. So i.e., what if x1 equals 4 and x2 equals 3? Then 3 times 4 equals 4 times 3. So if we did, this was x1, 1, 2, 3, 4, and this was x2, 1, 2, 3. Okay, I'm glad you guys are still here. There's a lot of different ways to do this. You either choose center of mass and then you don't have to write the G's, or you can try to actually work out the torques. And the torques are force times distance, right? So this is, last one was a man is standing on a diving board. The board is fixed in 2 points, 1 and 2. The board has negligible mass, which is fine. Which of the following is true about F1 and F2? So the way that I did this one is I chose the rotation axis in different places. So example, so choose rotation axis is, let's say, 1. In that case, then if you call this F2, and then this, I guess, the M of the man times G or something like that, then the torque of the man, this mg, is clockwise, so is negative. Okay, so to balance, the torque of F2 must be positive. So what that means is that F2 must be up. Okay, so that's choosing rotation axis equals 1. And then if I choose rotation axis equals 2, then the torque of mg is again negative because it's clockwise. And what this means is that the torque from F1 must be positive to balance. But the thing is, if your rotation axis is here, in order to get a positive torque, you have to rotate it counterclockwise, so it actually have to be down. F1 must be down. So that's the interesting thing, is that when you, so it's also see, when you have an object that's in static equilibrium, it doesn't matter where you choose the rotation axis. You just choose it wherever is convenient for you. And so in this question, since it's not rotating, right? So if it's not rotating, it doesn't matter where you put the rotation axis. It's not rotating about any axis. So if I chose point 1, it's not rotating around that axis, so I have to balance torques. If I chose point 2, it's not rotating about that axis, so again, I have to balance the torques. Okay. I find it's sometimes it's a little hard to kind of go through this and describe the theory of it. And the other thing is that if you read the textbook, it goes through it really clearly, I think. And so it is a very good idea to actually read the words of Eugenia Akina and how she does these things. I like to kind of go through some examples. So that's what I'm going to do in the time that I have remaining, about 10 minutes. So in equilibrium, an object has no net force and no net torque, because if it had a net force on it, it would be accelerating. If it had a net torque on it, it would be rotating. And the other way of saying is that its angular acceleration would not be 0. So you draw an extended force diagram, not called free body, force diagram, that shows where each force acts on the object. You set up your X and Y axes to define them, and you choose an axis of rotation. All these choices can be done to simplify your calculations. So it doesn't really matter. Each force has an X and Y component and a torque, so you sum all these up. And the equations are simple. It's the sum of the X forces equals 0, the sum of the Y forces equals 0, and the sum of the torques equals 0. There's 3 equations, and you can solve for up to 3 unknowns. Here's an example from the book. When you hold a ball in your hand, your bicep muscle tenses up and pulls up on your forearm in front of the elbow joint. When you push down with your hand on the desk, then the tricep muscle tenses and pulls up on the little protrusion of the forearm behind your elbow joint and rotates the other way. So that's what biceps and triceps do. And it's the equations of equilibrium which allow you to estimate what the actual forces are of your muscles on your bones. So the example problem from the text is that you're holding a 6 kilogram lead ball, MB equals 6.0 kilograms, the ball, with your arm bent as shown. The ball is 35 centimeters from the elbow joint, so I can draw this 0.35 meters from here to here. The forearm has a mass of 1.2 kilograms, and its center of mass is 16 centimeters from the elbow joint. So it's not exactly halfway, but there'll be a 0.16 meters. And there'll be the mass of the forearm, I guess, times G acting downwards. The question is, what is the force of the bicep on the forearm? And what is the force of the upper arm? So this bone, upper arm, on the elbow joint. And so the whole sketch and translate is you would draw it out, construct a labeled sketch of the situation. You wouldn't obviously have to draw it this fancy, but this is, again, just to speed things up, coming from the book. You'd choose an axis of rotation. Okay, I would choose the axis of rotation right here. Axis, oops, of rotation. In simplifying diagram, you kind of draw it again, but you draw an extended force diagram. So this is where you just sort of draw a rectangle and all the forces that are acting on the object. Decide whether you will model the system as rigid body or point-like. So in this case, it would be rigid body. You construct a force diagram, include the coordinate axes. So you put your Y and X here. Choose the axis of rotation, which you've labeled. Okay. Use the force diagram to apply the conditions of equilibrium. Once again, those are the sum of Fy equals 0, the sum of Fx equals 0, and the sum of all the torques with your pluses and minuses carefully chosen to be 0. You solve the equations for the quantities of interest and evaluate the results. Check whether the magnitudes are reasonable and whether they have the correct signs and correct units, and also see if they have the expected values in limiting cases. So in the case of this forearm, I can kind of try to draw it here. If this, again, is the axis of rotation, and we can draw it sort of being plus in that direction. You've got the force of the bicep. That's one thing that you're trying to find. So this is a question mark. Okay, this is for question A. And then you've got the force right here acting on the axis of rotation, the force of the upper arm is question mark, and that's question B. Okay, and then from here to here, you've got 0.16 meters, and that is showing you where the center of mass, the mass of the forearm times G is pulling downwards. And then from here to here, you've got the mass of this ball pulling downwards times G. And that's your, I guess, 0.35 meters. So I can define Y to be up, X to be to the right. There's no X forces, so that equation doesn't matter. You're only going to have two forces in this case because everything's just either up or down. So represent mathematically is just going to have the sum of the Y forces is equal to 0 and the sum of the torques is equal to 0. These are two equations, so you can solve two unknowns, which in this case is the force of the bicep, question A, and the force of the upper arm, question B. So the sum of the forces in the Y direction is equal to FB minus FU, because the bicep is acting up, upper arm is pushing down, minus the mass of the forearm times G, minus the mass of the ball times G equals 0. It's just a simple force thing that you've already done before. There's no distances involved in that. And so we can actually solve it out and say that FB minus FU is equal to G times MF plus MB. So we can call that equation 1 because we're going to use that later. If we can solve for either one of these now, we can solve for the other one. So since we've chosen the axis of rotation to be at the place where the upper arm acts, we are going to solve now just for the force of the bicep. And then we can use equation 1 to go back and solve for the force of the upper arm. So the sum of the torques is going to be 0. That's because it's acting at the axis of rotation, plus 0.05. That's this distance right here. And this is pushing up, so this is counterclockwise, FB. And then these other two are clockwise, so I minus the 0.16 times m of the forearm times g, and then I minus 0.35 times the mass of the ball times g. And then all these things equals 0, right? So I get that 0.05 of FB is equal to 0.16 times the mass of the forearm times g plus 0.35 mass of the ball times g. So the force of the bicep is equal to 0.16 times 1.2 times 9.8 plus 0.35 times 6 kilograms times 9.8 divided by 0.05. And when you divide by this 0.05, you get a big number, 450 newtons. So this is the answer to question A. This is a large force. It's much larger than just larger than, if you look at m, just mass of the ball times g is 60 newtons. The ball weighs 60 newtons, but since you're pulling up with the bicep, you have to exert a much greater force than just the force on the ball. It's sort of interesting. And then for B, we'll use equation 1, which we found before, which is that FU is equal to 450 minus 9.8 times 1.2 plus 6. I got that this is 380 newtons. Oops. People down out there. Candy, did you have a question?
Yeah, hi, good morning. So I have a question about the last question on the team up quiz.
Yeah.
So theoretically, could the center of mass be between the second pier thing and the man?
Yeah, this is a weird one. They said that the board has negligible mass. So in fact, I think the center of mass is the man.
Oh.
And then what's happening is that there's just these external torques, which are two external forces acting on this object. It's a big, weird object. It's like a very, very light diving board and a very heavy guy.
Oh, so if the center of mass is where the guy is standing,
yeah.
I don't really understand how F2 is pointing up.
Yeah, it's a weird one. The way I think of it is that F2 is what's supporting actually the weight of this person. But then it also has to support this F1 has to be kind of drilled into the ground to pull it down to keep them from just falling, right? So F2 has to be this very big force, which is equal to mg plus whatever this extra force is, the pulling force of F1.
Oh.
It's not a balancing point. The balancing point would be if you just held him up under his center of mass. When you don't do that, you need two forces that are in opposite directions.
Oh. So it's not possible for F1 to be the one that's holding everything up, and then F2 could possibly point down?
No, that wouldn't work. It would rotate then.
Oh, okay.
You'd have a non-zero torque.
Oh, okay.
I think this is the only way this works with to keep the torque zero. It's a good discussion though. Okay.
Thank you.
We can continue discussing, I think, if we want after class a bit. Basically, where we are here is it's reading week. Unless you have other classes today. So my advice is over the week, try to take a bit of a break. That's what I'm going to be doing. Try to get outside. At least the next couple of days in Toronto are supposed to be unseasonably warm. Don't forget to get some sleep. If you feel like going to sleep, you could always crack open the book and read through chapter 8. There will be a synchronous midterm assessment on Tuesday, November the 17th, which will be 2 problems using the 4-step method. One will be from chapter 7, one will be from chapter 8. You'll be using CrowdMark to upload an image or a PDF of your work. So that's it for me for now. I am going to turn off the YouTube and then see if there's any hands up for questions. So have a great reading week, and I'll see you on November 16th, bright and early.